Alright, so we've now seen that we don't actually need to use Pascal's triangle to work out the coefficients, because in fact there is this relationship between the combinatorics and Pascal's triangle. So NCK, we can use our traditional formula, n factorial and k factorial, n minus k factorial, if we want to work out a particular coefficient. Just going to prove that in fact NCK is indeed equal to n factorial on k factorial, n minus k factorial. Going to prove it by induction. The first case, however, won't be when k equals 0. For this, it'll be k equals 0. So we're going to prove it for k equals 0. Left-hand side, NC0 is equal to 1. That was our definition. The right-hand side, we get n factorial on 0 factorial, n factorial. But also, remember, we've defined 0 factorial to always be 1. So we get n factorial, which is 1. So yes, left-hand side does equal the right-hand side. So it's true for our first case. So I'm going to assume it's true for k equals r. R is some integer. So NCR is n factorial on r factorial, n minus r factorial. We're going to prove it true for r plus 1. So I want to prove NCR plus 1 is n factorial on r plus 1 factorial, n minus r minus 1 factorial. Okay. Remember, we have this relationship with Pascal's triangle, that n plus 1, CR plus 1, to get any particular one, we go to the row above, so n, and add the 2 above it. So NCR plus NCR plus 1. If I rearrange that, I can say, well, NCR plus 1 then is n plus 1 CR plus 1 minus NCR. But we've assumed NCR is n factorial on r factorial, n minus r factorial. Now, n could have been any number I picked. Remember, it's not n that I'm changing. It's k that we're changing. So I could have had n plus 1 there if I wanted to. So my assumption of n factorial could have just as easily been n plus 1 factorial. And so that's what I've substituted into the n plus 1 c r plus 1. Now, playing around with the factorials, the common denominator becomes r plus 1 factorial, n minus r factorial. And the top, our n plus 1 minus r minus 1, whoop, there it is, becomes n minus r. N minus r cancels with n minus r factorial. And that's what we're trying to prove. So hence it's true for r plus 1 if it's also true for r. And hence it's true for all positive values of n by induction. Okay, so the binomial theorem is what we're looking at. So what is the binomial theorem? There it is in all its glory. That when we expand out 1 plus x to the power of n, we get nc0 plus nc1x plus nc2x squared, all the way up to ncn x to the power of n. We can summarise that in some notation. So each individual term, so there's the general term, nck x to the k, and we're going from when k equals 0 up to k equals n. And nck is our standard n factorial, k factorial, n minus k factorial. Okay. Always keep in mind, there's always going to be one more term than the powers. So when you expand out your quadratic, you end up with 3 terms. Expand out a cubic, you end up with 4 terms, and so on. So there's always one more term than there are powers. And that's because, of course, you're starting at 0. So that gets you that extra term. 1 plus x to the power of n is not that useful. But, of course, we can extend that idea to a plus b to the power of n. The only thing we have to put in there is that now powers of a go down by 1, powers of b go up by 1 in each particular term. So the 2 powers will always add up to be n. So evaluate 11C4. Okay, I've lost my calculator. Oh, damn. We actually have to remember the formula. 11 factorial on 4 factorial, 7 factorial. In the good old days, we'd go, oh, well, the 7 factorial will cancel into the 11 factorial, and so I just have 11 times 10 times 9 times 8, and on the bottom 4 times 3 times 2 times 1. But there's a lot of cancelling that will happen there, because 4 2s are 8, and then 3 will go into the 9 3 times, and so I just get 11 times 10 times 3, 330. See, that's how we did it before calculators. We actually used our heads. It's quite clever. So we want to find the value of n such that NC5 equals NC8. Okay. Remember we got the one that says Pascal's triangle is symmetric. So if the n is the same, then NCK will equal NCn minus k. So 8 will be n minus 5, so n is 13. That must be the 13th row we're looking at. Or another way, I guess, of thinking about it is these two numbers, 8 and 5, must add up to give you the n. NC7 plus NC8 is 20C8. So this one's using the idea about, well, to create a term, we go to the row above. So logically, it looks like n would be 20. Oh, I was going to say 21 then. No, the one above would be 19, wouldn't it? So n minus 1, that's the theorem I'm using. So yeah, we'll get 19. Now, if I want to find the fifth term in the expansion, now that I've got a nice, neat formula, I don't need to expand the whole thing out. I just look at the general term and go from there. So the first thing in this sort of question is I'll say, well, what is the general term? Now, some people call the general term k, and then the first term becomes term 0. I personally prefer term k plus 1, so the first term is t1. It's just a preference, right? Because remember, the first term is actually when k equals 0. So if I use term k plus 1, I'll get 11ck. The first term, when I'm really writing this, I actually don't write the power down for the first term first. I actually write the power down for the second term. Because I'll go, oh, minus 3 on b to the power of k, and then I'll say to myself, oh, the two numbers must add together to give 11. So the other power must be 11 minus k. So we want term 5, the fifth term. Now this is why it's really important you keep the order correct. Because if I had started with the minus 3 on b powers being the highest, I'll get a different fifth term. So the actual order that they're written in the parentheses is important. If they say the fifth term, they mean that the first term will be 5a to the power of 11, not the minus 3 on b to the power of 11. So 11c4, 5a to the power of 7, minus 3 on b to the power of 4. Well, a lot of times with these questions, they'll allow you to leave it unsimplified. Because 11c4, 5 to the power of 7, 3 to the power of 4 is quite a large number. So that would be my unsimplified answer. If I did go and work it out, what's 330 times 78,125 times 81? It's, as you can see, a very, very large number. And to be honest, it's not that number I'm all that interested in. It's more what are the powers and things like that. Okay. So if I want to find the term independent of x, that's sometimes something that we find interesting, which is the one that doesn't have an x value in other words, the constant. What is the constant in this when we expand the whole thing out? So first step, I'll write out the general term k plus 1, so it'll be 9ck, 3x squared to the power of, well, I'll work that out later, minus 1 on 2x to the power of k. They've got to add together to give 9, so that other power is 9 minus k. If I'm finding the constant term or the term independent of x, that means the power of x must be 0, because x to the power of 0 will give me 1. So when I'm working this out, I don't worry about the coefficients. I'm just looking at the powers of x. So I'll have x squared to the power of 9 minus k, and I'll have x to the power of negative 1 to the power of k, and I know that's going to be x to the power of 0. And that'll allow me to find which term it is we're interested in. So if I expand that out, we get 18 minus 2k times x to the minus k, 18 minus 3k, add the powers, remember. K turns out to be 6. So it's not the 6th term, it's actually the 7th term using my notation, because I'm going with the term k plus 1 notation. And term 7 would be, now I can substitute back in, well, I know all the x's will cancel, so I'm left with 9c6, 3 cubed over 2 to the power of 6 would be the independent term. All right, there we go, let's play with 5D.